Hello everyone. We are now ready for our final analysis of Darcy's law. In the previous two lectures, we were looking at Darcy's law in one direction, one dimension I should say, either through a homogeneous piece of soil or rock or through a layered system, but the flow direction was just one-dimensional. And so now we are going to look at Darcy's law in multiple dimensions, because when we run a groundwater model, it's a multi-dimensional water. It's not just, the water doesn't just flow in one direction, it goes in all directions. And so in order to set things up so that we can derive our governing equations, we need to have a way of expressing Darcy's law in multiple dimensions. So, first of all, we are going to look at an isotropic medium. Isotropic means the properties are the same in each direction, and we're going to look at this in two dimensions. So we have x and y, and so K, the hydraulic conductivity in the x direction is the same as the hydraulic conductivity in the y direction. Now this actually, if you consider y to be vertical, this almost never occurs in practice. There's typically kx does not equal ky, but just to handle this simple case mathematically, what does this look like? And so to do this, to represent this circumstance, we simply write Darcy's law once for each direction. So the flow in the x direction is equal to minus k del h del x. And remember, we can represent Darcy's law either as q equals kia or v equals ki. Q is the volumetric flow rate and v is the Darcy velocity. And in this case, we're using the velocity term. And we're also representing it using the derivative form. So instead of ki, where I is the change in head divided by length of flow, we say minus del h del x, where that del h del x is the hydraulic gradient in the x direction. And since we're going from high head to low head, that's a negative gradient, and so we have to put another negative sign out front to cancel that. And the Vy is equal to minus k del h del y. So another way to state this is the flow in the x direction is equal to the hydraulic conductivity times the hydraulic gradient in the x direction. The flow in the y direction is equal to the hydraulic conductivity times the hydraulic gradient in the y direction. So, so far, very simple. Now, what happens when we have an anisotropic medium? So, this is, again, simple case, 2D. But now, since we have bedding planes, the hydraulic conductivity in the x direction does not equal the hydraulic conductivity in the y direction. And if the bedding planes are oriented as shown in this diagram, kx is going to be much greater than ky. In fact, we typically have a ratio of 3 to 5 or more, meaning the hydraulic conductivity in the x direction is usually 3 to 5 times what it is in the vertical direction, based on these bedding planes and the how the math works out and how water flows through layered systems, as we learned in our previous unit. So now in this case we write things a little differently. Basically we just plug in the appropriate hydraulic conductivity. So Vx is equal to minus Kx. The hydraulic conductivity in the x direction times the hydraulic gradient in the x direction. Vy is equal to minus the hydraulic conductivity in the y direction times the hydraulic gradient in the y direction. So far so good. Now let's talk about the general case. Now, the simple case means we have horizontal bedding planes. In the general case, those bedding planes may be tilted at some angle. And how do we represent Darcy's law in this case? Water may or may not be flowing parallel or perpendicular to the bedding planes. The water could be flowing in any direction depending on the hydraulic gradients. So how do we represent that? Now, by the way, if the bedding planes are dipping at an angle shown here, the maximum hydraulic conductivity will be parallel to the bedding planes, and the minimum hydraulic conductivity will be perpendicular to the bedding planes. And so we can come up with a second rotated coordinate system that is aligned with these bedding planes using a K-min and a K-max term. That's important as we go through this little derivation. However, we could just do a coordinate transformation, but we need K in terms of both X and Y. And so if we first derive Darcy's law using this rotated coordinate system that's aligned with the, by the way, we call these the major and minor principal axes of hydraulic conductivity. So Kmax in the R direction would be the major axis of hydraulic conductivity, and Kmin in the S direction would be the minimum axis of hydraulic conductivity. So looking at that system, the Darcy velocity in the R direction aligned with Kmax would be minus Kmax del H del R, the hydraulic gradient in that direction. And V sub S, the Darcy velocity, this is not seepage velocity, this is the Darcy velocity in the S direction, would be minus Kmin times del H del S. We can put these into matrix form. As you may recall from linear algebra, VR would be equal to minus Kmax times del H del R plus 0 times del H del X. And then Vs is equal to 0 times del H del R minus Kmin times del H del S. So this matrix formulation is equivalent to these two equations. And this part here is called the conductivity matrix, or the conductivity tensor. And it is symmetric. It's banded and symmetric, meaning it's symmetric about the diagonal, and then the off-diagonal terms are 0. Okay, so this R and S may or may not correspond with X and Y. If it corresponds with X and Y, we're done. We just replace Kmax with X and Kmin with Y. But if it doesn't, we need to go a little bit further here. And to do that, we perform a coordinate transformation. So first of all, we have to define a relationship between the S and R axes and the X and Y axes. Remember, R is the direction in which the hydraulic conductivity is the greatest. That would be the parallel to the bedding planes. And S would be the direction in which the hydraulic conductivity is the smallest, and that would be perpendicular to the gradient planes. And so if the R is rotated in the direction shown here, that would be a positive angle alpha. If it's dipping down the other way, that would be a negative direction. And so this case that we saw back here would be, I don't know, a negative 45 or something. And so that is how we define that angle. And then in the most general term, we can define Darcy's law in the general case in matrix form as shown here. Now the off-diagonal terms are not 0. And if we multiply through Vx is equal to minus Kxx times del H del X, the hydraulic gradient in the X direction, minus Kxy times del H del Y. So Vx is equal to this term times this, minus this term times this, and that's how we get that equation. And this is similarly Vy is equal to minus Kyx times del H del X minus Kyy times del H del Y. And so now we have a truly general form. And by the way, this Kyx and Kxy, these are called the off-diagonal hydraulic conductivity terms. This, as you go in this direction, Kxx, Kyy, that's the diagonal. These are the off-diagonal. And Kyx is equal to Kxy. So this, again, this matrix is symmetric. And so Kxy is equal to Kyx. So another way to think of this, before we go on, the Darcy velocity in the x direction is equal to the hydraulic conductivity in the x direction times the hydraulic gradient in the x direction minus this somewhat different hydraulic conductivity times the gradient in the y direction. So since the bedding planes aren't aligned with x and y, the hydraulic gradient in the y direction can have an impact on the flow in the x direction. And likewise, the flow in the y direction can be impacted by the hydraulic gradient in the x direction, multiplied by this off-diagonal k term, and then, of course, it's also impacted by the hydraulic gradient and the hydraulic conductivity in the y direction. So there is, if you think about it, it makes some sense intuitively as well. Now, how on earth do you come up with these terms? And let's assume what you start with is K-min and K-max. If we're going to measure or estimate hydraulic conductivity, it's much easier to estimate it parallel to and perpendicular to the bedding planes. We can just plug in our layered system K equivalent terms. If we have an estimate of K in the individual layers and the thicknesses, it's not difficult at all to get an equivalent hydraulic conductivity parallel to the layering in the R direction and perpendicular to the layering in the S direction. But then we need to transform that into this hydraulic conductivity matrix, and there's actually a way to do that. I could show you. The derivation is rather long. It's part of a coordinate transformation, but if we just solve in terms of Kr and Ks and the angle, Kx is equal to Kr times a cosine squared alpha plus Ks times a sine squared alpha. Kyy is Kr times sine squared alpha plus Ks cosine squared alpha. There's some symmetry there, as you can see. And then Kxy is equal to Kyx is equal to minus 1/2 Kr minus Ks times the sine of 2 alpha. So the bottom line, if you know what Kmax and Kmin are, parallel to and perpendicular to the bedding planes, or if you have a way of estimating that, using these equations, you can derive a full hydraulic conductivity tensor for Kx, Ky, and the off-diagonal terms. So that's how we do it for 2 dimensions. Extending this to 3 dimensions is actually fairly easy. Now we just add that third dimension. So now we've rotated the coordinate axis a little bit. X is horizontal, Y is horizontal, and Z is vertical. And assuming that our bedding planes are primarily horizontal, typically Kx is equal to Ky because you're in the same horizontal plane and you're parallel to the bedding planes, but Kz would be much smaller because it's flowing perpendicular to the bedding planes. Although it can be the case that all three of the hydraulic conductivity is different in all 3 directions. But if the x, y, and z axes coincide with the principal axes of permeability, which happens, if you have horizontal layering, that is true, because then x and y are Kmax and z is Kmin. the hydraulic conductivity matrix, or excuse me, Darcy's law matrix looks like this. Vx is equal to minus kx del h del x, Vy is equal to minus ky times del h del y, and Vz is equal to minus kz times del h del z. So you're just coming up with a simple representation of Darcy's law in each dimension. So that's pretty easy and straightforward. But in the more general case, and this is what I mentioned before, in most cases kx is equal to ky, and kx is greater than kz, or kz is smaller than both kx and ky because of the layering we talked about. This is the more general case. We have a full hydraulic conductivity tensor. The diagonal terms are kx, ky, and kz. By the way, in practice, we often just write kx instead of kxx. But when we're showing the full matrix, this kind of makes sense. And again, the tensor is symmetric about the diagonal, so kyx is equal to kxy, kzx is equal to kxz, and kzy is equal to kyz. Furthermore, if you want, in this case, the individual terms would be, for example, Vx would be equal to minus kxx times del h del x, minus kxy times del h del y, minus kxz times del h del z. I will say, while this is the more general case, when we get to mod flow, what happens in mod flow is mod flow kind of, one of the assumptions in the governing equations for mod flow is that your x, y, and z axes coincide with the principal axes of permeability. And so there are no off-diagonal terms. Other groundwater models allow you to have off-diagonal terms, but mod flow assumes that this relationship holds. So that's kind of a simplifying feature of mod flow, but when we get to where we're deriving our governing equations in our next lecture, we're going to be using this full 3D case to derive the most general form of our governing equation that we solve in groundwater flow systems. So there you have it, Darcy's law in 2D and 3D, in both the case where the coordinate axes are aligned with the major and minor principal axes of hydraulic conductivity, and when they're not. And by the way, just a note, if you do see a case where the off-diagonal terms are not zero, as shown here, then you just remember that, well, that alignment does not take place, but if they are zero, then we know that that alignment is occurring. And we'll revisit that principle more as we go through the derivation of the governing equations in our next lecture. So that's it. Thank you.